I believe it is now, 12 o'clock. Hi everyone, hopefully you can hear me. I'm Alistair Willis, the Marketing Director for Geobear in the UK. And with me today is Andy Lee, our Vice President of Engineering. And this is a Geobear webinar where Andy's going to talk about essentially the fundamental principles behind geopolymer or geopolymer engineering, if you like, and some relevant case studies to you who work on infrastructure and structures. So hopefully this will open your eyes if you're not aware of Geobear or geopolymer solutions in general. There is going to be a Q&A afterwards. So if you've got any questions as we go through, type them in the box in the bottom right-hand corner, and I will pull those up on screen, and then Andy will do his best to answer those for you. So I'm just going to hand straight over to Andy now to run you through the main presentation, and I'll be back later on when it's over. Over to you, Andy.
Okay, thank you, Alistair. Okay, so who is Geobear and what do we do? We're a global leader in non-disruptive solutions for foundation and infrastructure settlement and substance problems. It's a global business established in the early 1980s in Finland. Our company was originally known as Eurotech until December 2017, before a global rebranding exercise was undertaken. UK business was established in 1989, and currently we have offices in London, Wolverhampton, Winchester and Sandy. We have a full in-house design team. We also work with third-party consulting engineers and materials testing labs. And globally, Eurotech type solutions using geopolymers have been used on over 200,000 projects worldwide. It's probably closer to 250,000. So where are we located? Our head office effectively is in the UK, where we do a large percentage of our business, but we also have offices in Sweden and Finland and in Poland. Plus, we operate in China and the USA, and we're currently in the process of setting up an office in the Middle East, in Dubai. So what sectors do we operate in? Highways, commercial, residential, utilities, energy, airports, ports and harbours and railways. So most major sectors of the construction industry. And what sort of problems do we solve? So here's an idea of the sorts of things we come across. Things to do with unstable slabs, subsidence of concrete pavements, bridges and bridge abutments, voiding, cases of natural man-made voiding behind walls due to solution features, water ingress into deep excavations, and we deal with containment of contaminated soil can be done, groundwater cut-off systems, bulk void filling, densification of loose granular materials and strengthening of soft soils to increase bearing capacity, reduce settlements, realigning track beds, and dealing with subsidence due to clay shrinkage. These are some of the major areas that we operate in. So let me introduce you to a little bit about what geopolymers actually are. Some people may not be aware. So the Geobear geopolymers we use are a multi-component structural resin, which has been developed specifically for ground engineering applications. The geopolymer mix is injected into the ground under pressure as a liquid and undergoes an exothermic chemical reaction. This induces a state change from liquid to solid. It is the consequential increase in volume which produces the dynamic energy and subsequent expansive force. And this compacts the soil or strengthens the soil. The chemical reaction is very quick and immediate, resulting in solid compound that possesses definitive physical chemical characteristics. Geopolymer reaches 90% of its final mechanical characteristics in less than 15 minutes. And as a result of research, we have multiple polymers that can be used for different applications. Here's a little picture of a lab test just to sort of show you what happens when you mix the two components together. We have the two A and B components, which when put into a cup and mixed, after a certain amount of time, a chemical reaction occurs and you get a volumetric expansion. And this is on the bench in the lab. You can see a significant increase in volume. With conservation of mass, we have a reduction in density. So geopolymers are generally low density materials. I think we have, here's a graph that shows in time how the expansion occurs. So these are the key things we need to know. The cream time is the time which the mixture is waiting to react, and that's controlled by surfactants and other agents within the mix, accelerants and catalysts, and they affect the timing of the reaction. So some polymers are very, very fast reacting, a matter of seconds, a few seconds, and other polymers are longer reacting, maybe 30 seconds or even a minute, depending on the application. But essentially, after that cream time, the reaction then commences and the polymer then expands, and there's an increase in viscosity as the mixture goes from liquid into solid, and that's shown on the graph in terms of showing the expansion in volume that occurs over time. So that shows you in a graph. There is a very small clip which Alistair will play that shows you of injecting of a polymer, liquid polymer, into a void. And here the liquid is entering during the cream time, and now the reaction starts. And there's a rapid expansion of the actual polymer. So what you saw there was a specific polymer used for expansion into voids. We use a highly reactive polymer that rapidly expands into voids. For other applications, and I'll come on to those in a minute, for ground improvement, ground stabilisation, while you're injecting into soil, then we have a different reaction profile. And this shows you a cross-section of the reacted polymer, and you can see it has a foam-like structure. So the circles that you can see, that is the actual hardened resin, and inside these spheres is in fact carbon dioxide. So the chemical reaction releases carbon dioxide as a driving force of the expansion. So that's why it can expand. It's the generation of CO2 during the chemical reaction that's bound within the structure that causes the expansion. So that's how it works. Now we can take our samples to the lab and we can test their strength. So we know what the performance of the material is at any given density. Geopolymers are non-linear materials, which means their strength varies with their density. So depending on what density is achieved when you inject, you get a different strength. And we have means and methods for calculating in situ density from which we can calculate in situ strength. All I would say is that all of our polymers from our manufacturer are tested, and so we know what the performance is from a strength point of view over a density range that we would apply the polymer. We've had our polymers tested extensively to see whether they potentially leach any harmful contaminants to the environment. We've had them tested in the hard format, and we've had them tested during the reaction phase, during the liquid phase. And we found that there's no compounds are released above laboratory detection limits with respect to sort of the EQS standards in the UK, that's environmental quality standards. So there is no risk to groundwater from these type of materials. They are generally speaking in the polyurethane family of materials, and polyurethane type foams are widely used in the environment, you know, whether they're for clothes or shoes or used in construction of building materials, and are used in cars. So polyurethane type materials are widely used. We use specialist ones for injecting into the ground. So they're not uncommon materials. So we are utilizing something which is well known and well understood in terms of any risk to the environment. We've also had a look at sustainability. It's quite important that we move towards more sustainable construction techniques. And we've had our geopolymer solution benchmarked against other traditional solutions. Now that would be, let us say, a traditional underpinning or piling solution for a residential property, and you can calculate the carbon that you would use for a traditional mini piling scheme, or for a reinforced concrete underpinning scheme, and compare that against improving the ground using geopolymer, and you generally get about 53% less carbon released using geopolymers. This is partly due to that we use a lot less material, and also because we do the work very quickly. So most of our projects, certainly in the residential market, are covered in 1 or 2 days, versus several weeks of a traditional underpinning scheme. For infrastructure projects, pavement replacements, and for level crossing replacements in the rail sector, the savings are much greater. And that's because we can retain existing structures, we can retain existing pavements or concrete slabs, and improve the ground underneath them, so that you don't need to dig up the slab, dig out the poor fill, put back, compact, and then reconstruct the slab on the top. We can avoid all of that just by injecting polymer into the ground and improving the subgrade performance. I'll come on and show you how that works in a minute. On our website, we have a general capability matrix. You may not be able to see the detail here at this scale, but it's available on our website. And it runs through the typical sort of solutions that we can provide in terms of bearing capacity improvement, re-leveling of slabs, clay shrinkage treatment, void filling, water sealing. And it gives the sort of general limitations of our method and what we can and what we can't do. And that might be a useful guide if you're thinking about using geopolymers as a means of improving ground conditions against other more traditional methods. And it includes things like slope stability improvements, mitigation of liquefaction risk. There is a range of different things that we can do, all in the ground improvement area, improving ground conditions underneath existing foundations and structures, such that you do not need to create a new deeper foundation or a piled foundation or something similar. And I'll go through some examples in a minute of a few case histories of how it's been applied. And you can see how that might apply to a problem you have to solve. Can you solve the problem with the geopolymer, which is a very non-disrupted method? And in general, I will show how it's installed through small diameter tubes using lightweight equipment, no need for heavy construction plant. And it really is very good for tight access scenarios. So let's just explain a little bit about how it works. I mean, all engineers want to know how things work. And so I'll try and explain best I can how the basic principles of how geopolymer works. Here we have a picture on the right-hand side of some geopolymer injected into a soft clay. And the white lines in the picture is the actual geopolymer, and the grey soil and the yellow soil is behind it. And on injection, the geopolymer essentially hydraulically fractures the clay, because we're talking soft clay. It hydraulically fractures it, and our geopolymer then migrates along that fracture, filling it in with geopolymer. And within that fracture, the liquid polymer undergoes a state change from liquid to hard solid polymer. The solid polymer reinforces the soft clay and increases the bearing capacity and the stiffness modulus. So it's akin to putting rebar inside concrete to reinforce it, it really is it adds a significant amount of stiffness to a soft clay, whereas the compressive strength of our polymers can run up to sort of 5 megapascals compressive strength, which is really quite high compared to the strength of a soft clay. So it's a reinforcing methodology of putting in reinforcing into the clay to make it stronger. I'll talk briefly about something called equilibrium pressure for those technical people. One of the key things for us to be able to design ground improvement is we need to know how strong the polymer is going to be in the ground, such that we can calculate a revised bearing value. So essentially the polymer strengthens the clay on a volumetric ratio. So it's a volumetric ratio of polymer to soil, and the relative strength of the polymer and the relative strength of the soil. And by taking the average of the two on a volumetric basis, you get an improved strength of overall clay. And in order to do that, you need to know something called the equilibrium pressure. And that's the point at which the expanding polymer in the soil is in equilibrium with the confining pressure of the surrounding soil. And so there's some fairly advanced maths behind the calculation of this type of theory, and most of it has been done by a guy called Manacero in Italy. There's publications on how this can be done and all the equations behind it. But essentially, that we need to basically predict the strength of the polymer in the soil based on assumptions about how it expands. And here's an example from one particular case that we've looked at, where we had a very soft clay on this site, and the blue line was the undrained shear strength before the injections, and the red line is the undrained shear strength after the injections, and there's around about a 250% improvement. And the black dots on the graph is what is our model prediction as to what performance we would get. And essentially, we use a model to calculate how much polymer we need to put in, what type of polymer, and the spacings of the injections in order to get to a desired outcome. And there's a good result here. And we have many case examples where our predictions turn out to be correct. Let's look at granular soil for a minute. Sands and gravels are obviously different to clays with much coarser grain size. And so when you have a coarse grain soil, the initial movement of the polymer is to permeate through the pore space. So it flows as a liquid through the gaps in between the soil particles. It doesn't create fractures. So it permeates and forms what I would call a bulb. And after a certain amount of time, after the cream time, it starts to expand. And so you get expansion, and it forms a bulb of polymer rather than a fracture. And here's a picture of a bulb done in a test facility. And you essentially compact, what you're now doing is compacting the soil, because the volume expansion pushes the soil out of the way and essentially is compacting it due to expansion. There's a little graph here that sort of shows the three stages of the injection into granular soils. So there's the initial permeation, then there's active expansion phase, and then what we get is called the plastification zone. And so that's the area outside of the actual polymer bulb itself that's been physically deformed. So you essentially have a hard bulb of polymer, but outside of that bulb, there's also a zone where the soil has been deformed or compacted. And so when you put these bulbs together in a row or in a grid pattern, you get densification in between the bulbs. And the bulbs themselves are very strong, but the weakest point is in between the bulbs. And so we design our solutions on the weakest point, which is in the center of where the bulbs are. So this shows you how you can get densification by using a grid system of injections, because our injections are normally done on a grid basis or on a linear basis. You wouldn't do a single injection. You'll normally do a series of injections. And here's some granular compaction results. it shows that the before and after compaction as measured using dynamic penetration testing. So a very simple of counting the blows. So dynamic penetration testing, or DCP testing, is quite common, where you knock into the ground a cone of a certain diameter using a mass and dropping it over a fixed height and counting the blows. And we can get good improvement in terms of the blow count, and the blow count relates to the density, and the density relates to the angle of friction, and the angle of friction relates to the bearing capacity, and this is really how it all works. So there are some applications that we can look at of how can I apply this to problems that we might have. And so let's look in a little bit more detail of how you can apply this technology. So here we're looking at looking at a road or a track bed, a concrete track bed, and under dynamic loading, voids can develop under slabs, and this can be on roads, railways, airfields, and this is due to subbase erosion. This is just a dynamic load from the vehicles or whatever machines are moving over the concrete pavement. You can develop voiding under the slabs. The erosion is as a result of either soft underlying conditions, or it might be combined with poor drainage. And this can lead to structural cracking of the slab and pumping, loss of fines and cracking. This is quite a common phenomenon. So we can treat this by slab stabilisation. And so this just shows a little picture of some of our team in the field. You may be able to see on the picture some small tubes. We essentially drill a 12mm diameter hole and install an injection tube through which we inject the liquid geopolymer. And then we monitor the injection of the polymer using a laser level because the expansive nature of the geopolymer will tend to lift the ground or lift the structure. And so this is how you would stabilize a slab with voiding: is you drill a series of holes, you put in the tubes, you inject the geopolymer, and then you look for a surface reaction to know that once the voids are filled with polymer, and you know they're filled because you start seeing the ground lifting. And we can control the level of injection to less than 0.5 millimeter accuracy, because often we don't want to overlift if we want to maintain the same level. If there's been significant settlement, then we can over-inject and raise the slab to a new level, depending on what is required, what the target level is. But you can see that the injection is done using very lightweight equipment and with minimal disruption. And so we can do the work very quickly, get in and get out without the need for long possessions or road closures, and improve the conditions underneath the pavement, underneath the slab, and thereby extend its life. This shows you a little drawing, cartoon drawing, if you like, of a void under a slab, and we just drill a hole, put the polymer into that void, and it sort of works. There's a picture there that shows we got a camera inside underneath the concrete slab. You can see the sort of polymer expanding as it migrates through that void. And at all times, we control the amount we put in by using laser levels so we don't overlift. And so that's easily controllable in terms of the amount of kilos you put in every second. So that's how you stabilize slabs. Other things you can do, I said that these polymers are expanding polymers, so they generate lift. So we've been involved working on pipe work, transmission lines, which are supported on pad foundations, such things like large diameter gas pipes, quite heavy, and they're normally supported on pad foundations. And over time, they can suffer from settlements if the ground conditions are poor. And we've been involved injecting polymer underneath those pad foundations that are supporting gas pipe infrastructure and re-level it and lift it back up to where it was. And so this can be done again using laser level control to lift lift structures. There's a case I've recently been involved in Sweden where we were lifting some fairly large pad foundations to a warehouse, and the total weight lifted was about 55 tons on a large pad foundation. So, and that was lifted about an inch, so 25 millimeters. So we can lift relatively heavy loads. So lifting a pipe work that's nowhere near 55 tons, or was that 550 kilonewtons in those units. So really quite heavy loads can be lifted. Now there's something here about subgrade strengthening, and this is to look at the subgrade underneath your track bed if you've got a railway, or underneath your road. And there's lots of testing been done that shows that you can essentially treble the soil modulus by injecting polymer. And here's some testing done by the Australian Institute of Technology, who looked into, they were using falling weight deflectometer results to see how does the dynamic modulus improve after polymer injection. And here's a test in a larger sort of concrete test cell. So this is really looking at railway applications. So the thickness of pavement or railway track should be designed so the subgrade is protected adequately. How this is not always possible is due to undetected soft spots, budget constraints, or excavation constraints. So sometimes you can't get enough protection over the subgrade. And so one solution then would be, instead of introducing a large amount of fill on top of the subgrade, why not make the subgrade stronger? So it needs less protection. And this is a similar concept with a road pavement, is that, you know, that under wheel loading, the subbase is stressed if the base layer is very thin. And this is due to failure of the subgrade. So the one obvious solution is to put polymer into the subgrade, make it stronger, such that the subbase can be thinner. Here's an example. So subgrade improvement. This is showing how you could get a 35% reduction in subbase materials with geopolymer injection. So you may have had a CBR of 3% before that required a certain thickness of materials. And if we can inject geopolymer, that is effectively going to raise the CBR, such that you can then use a shallower thickness of material. So this saves money, and in the long run also reduces the amount of materials you're going to need. So it's going to be a lower carbon solution. Bearing capacity in foundations. So I've talked about shallow treatment. I've talked about injecting underneath slabs to re-level them. I've talked about strengthening subgrade under pavements, under track beds. You can inject deeper than that. You can go to several levels of injection. And the objective here is to densify and strengthen the soil under foundations. So we can improve the bearing capacity of soil under structural foundations by injecting polymer. And we select the different polymer depending on whether it's granular soil or whether it's cohesive soil. And for most loose or soft soils, we can generally double the bearing capacity really quite economically by doing enough treatment under the foundations to stiffen up the soil, thereby increasing the bearing capacity without the need to alter the dimensions of the foundations. You don't touch the foundations. You don't need to make them deeper or wider. You can just make the soil on which they sit much stronger. Slope stabilisation. This affects highways and railways, and it can be in any scenario where you've got a constructed slope, embankment, and they often fail for various reasons. Poor infill materials, poor compaction, inadequate drainage, excessive water pressure, or poor vegetation management. there's lots of things that cause slopes to fail, but essentially it's entirely possible to strengthen the material in the slope using geopolymer injection to mitigate against slope failure. And here's a few examples of the case of the types of slope failure you might see. And then here's a solution that we might be able to put polymer into the embankment, thereby increasing the shear strength or increasing the angle of friction, and that will mitigate against the effects of slope failures. So that's another application that you could apply this solution to. There's something called transition to structures. This is more applicable really to a rail scenario or a road scenario where you're moving from an embankment onto a structure or a bridge, and so there's an abrupt change in the stiffness of the soil as you go from soil into concrete foundation, and there's often settlement immediately in front of the structure. And this is because of the rapid change in soil stiffness as you go from soil into structure, and it's a particular problem on railways as they approach bridges. And so, how can this be solved using geopolymer? Well, what you need to do is, if you're transitioning into a structure from an embankment, what we can do is to increase the shear strength of the soil or the density of the soil in zones as you approach the structure, so you can transition and essentially make the soil get stiffer as you approach the embankment. And this is by doing either deeper injections or higher massive injection the closer to the structure you are, so there's not such an abrupt change from soil to bridge. So it's a way of trying to mitigate the differential movement. And here's an example on a road bridge of the set out of the injection points to try and mitigate against that sudden change from soil to concrete. So this is transition to structures. I've now got a few case histories of real jobs that we've done that I can take a little bit of time to go through, and in order to leave a little bit of time for the Q&A at the end, because I've been through the sort of theoretical part fairly quickly. So I want to talk about some real world cases that we've worked on. Now, I'm going to talk here about a slope stability situation first. And this relates to a railway, they called a historic railway in Shropshire, called the Severn Valley Railway. And it's essentially a privately owned railway that's used for tourist purposes, and they run old locomotives on it. Sort of legacy trains are run on this line. However, this particular line is quite an old line and is showing signs of distress. And there was about a 300mm deviation from the design geometry. And this introduced a significant speed restriction on this part of the line to only 10 miles per hour. The distress can be seen in the picture. You can see the substance that's affecting the tracks. They're not straight, and you can see them deformed. Now, the track deformation appeared along approximately 80-metre long section on the western side of the River Severn in Shropshire. This was the problem. And what I'm going to show you now, this is a cross section through the railway embankment, which is shown on the right-hand side of the picture. Essentially, we're in a valley here, so there's steeply slided valley. At the bottom of the valley, there's an embankment along which the train runs, and then a bit further down, there's then a river. So we're in a river valley. So the actual railway was built on an embankment comprising of ash fill material with a mantle of track ballast at its crest, and it forms like a small embankment at the bottom of this steep slope. The maximum height of the embankment was about 4 to 5 meters, so we're not talking a very large embankment. It was just where it was located there was a problem. It doesn't appear from this profile why it should be in such a large amount of distress until you look at the underlying geology. And what we had a look at is that the geology of this actual site is the embankment itself was placed on top of what's called a weathered mudstone, and the weathered mudstone had turned into a clay. And within that clay, there was a line of weakness due to an historic landslide. So there was essentially a shear zone in this clay on top of which the embankment had been placed. And so it wasn't necessarily the embankment fill material that was the problem. It was the underlying clay material. And there's a line of weakness within that clay due to an historic landslide. Now, in order for us to confirm that, we were given a site investigation. And so we built a Plaxis model to see if we could replicate the movement that was being shown, and then sort of try and determine what the factor of safety was of the overall embankment. And this shows the sort of the Plaxis model that we developed, and the model confirmed that the position of the shear zone and the movement along the shear zone. So we essentially had a layer of very, very weak clay along which the whole embankment was sliding over towards the river. And so the treatment design was to focus on strengthening this weak layer. It wasn't really the whole of the embankment. The real issue was a particularly weak layer underneath the embankment. Now, the design solution for this was developed using Plaxis, and it was developed by incorporating the effects of the geopolymer injections into the different sections of the embankment. And the configuration is shown on this drawing. So you can see we identified in the red dashed line the critical area that injections need to be placed. You could, if you liked, treat the entire embankment, but we only were targeting the minimum amount of work to see if we could stabilize this part of the railway using the minimum amount of materials rather than the maximum amount of materials. This shows a cross section of what an injection plan looked like. This was on a test section, and you can see there were several layers of injection vertically and also horizontally along the railway line, with the main area to get down to the shear zone, which is shown on the bottom of the section. This was a key area we needed to get some polymer into. This shows how the work was done. Work took place last year, 2022. We had a mobile injection unit attached to a train, and then we drilled 12mm holes through the soil down in between the railway tracks into the underlying soil. We used a total of 136 tubes, and we used what we call an extraction method. We injected roughly 2.5 tons of material into the slope, and we verified the performance on the day using pre and post dynamic probing. And we also had tilt sensors on the actual railway track to measure the tilt before and after our treatment. And the work was done in 2 10-hour shifts. So it was very quick. And the alternative to this solution would be essentially to rebuild the entire embankment, which would have taken months. So this was a very, very quick solution. And here we have some test results, before and after test results. And what these results particularly showed was that using lightweight penetrometer testing to look at the immediate effect of injecting polymer, is we got a significant increase in shear strength after the injections. I think in the shear zone, the sort of strength of the clay measured using penetrometer testing was of the order of 10 to 15 kilonewtons a meter squared, so very soft. And after we'd done the injections, the shear strength was averaging around about 75 to 80 kilonewtons per meter squared. So we had a significant increase in the undrained shear strength, which would in fact translate into higher drain shear strength parameters, adding some cohesion principally to the stability of the slope. We did some testing using there was an inclinometer that and the inclinometer treatment had sort of showed that the rate of deterioration had greatly reduced before and after the treatments, and the measurements were indicating the rate of movement had been reduced by 72%. Because it was only a test section, we didn't do all 80 meters of the embankment. There was still some residual movement, but significantly less than the previous condition. And it did actually enable the railway line to be reopened at a slightly higher speed. And the customer was very happy. So let's have a look at another problem. This is to do with stabilisation of a sewer. So this is a large-scale sewer that was leaking due to displacement on joints, and that led to subsidence at the surface due to the sewer sinking, and it was causing damage to the road above and was causing major disruption in the local area. So this shows a BIM model of the sewer that was settling due to the leaking pipes. And so we were then asked can we inject polymer underneath this structure, buried structure, lift it up or stabilize it as a minimum, such that the road could be relaid level and there wouldn't be suffering from a localized subsidence issue. It was in a busy local area next to a supermarket, so there was a lot of disruption caused by damage to the road. So it was quite important that the job was done very quickly. We worked very closely with the Anglia Water on this case to construct a BIM model that shows where all of the injection points were going to be before we injected them. And this was primarily to make sure we avoided drilling into the sewer and avoid all the services. There's a lot of buried services in this general location. We want to be quite careful we missed any services with our drilling. So there was several hundred holes drilled all around this structure, and then polymer was injected underneath it. After the injections, we verified the performance using standard penetration testing, and what you can see is before is in blue, and the SPTs in some cases were 0 or 1s. I mean, very, very loose ground because of the leaking water. And after we'd done the treatment, we'd sort of increase the average SPT values, so something of the order of 8 to 10, which was a very significant improvement over what the condition was before. And further to that, we then went and had a look at some satellite data to see how things improved. So this was using some satellite data that was purchased for this particular section of road. And you can see over time prior to the treatment, the levels on the road were continuing to drop quite significantly over a period of weeks and months. And after the stabilization work had been done, we then had essentially arrested the continuing settlement of the road. So that sort of confirms, from the density improvement and also satellite monitoring of the road level, that it had been stabilized, all done in a non-disruptive manner. There's some work here at London Heathrow Airport. This is improving bearing capacity underneath the foundation. So at Terminal 3, the building foundations were originally designed on an allowable bearing capacity of 160 kilonewtons a meter squared, and therefore there was a requirement to add an additional floor to the building, which would lead to an increase in bearing capacity. And rather than construct new foundations, deeper foundations, or even a pile foundation, we were asked if we could increase the bearing capacity underneath existing foundations so that the additional story could be added onto the building. And so it involved 14 pad footings with required extensions. The extension involved adding concrete flanges to the existing foundation to increase their footprint, but there was no need to go deeper. And so that was a foundation option, and that would have required, this is the alternative strategy, this would have required major excavation, temporary works, and a lot of disruption in the building to actually make the foundations bigger in order to carry the additional load of another floor. And so rather than doing all this extra construction work and excavation work, we're asked, can we just inject under the foundation, make the ground more dense? And so we came up for a couple of options here, and that was to drill through the existing foundations at various points within the footprint of the foundation and to inject our polymer at different levels. One of the important considerations is that they didn't want any lift. So we had to increase the bearing capacity without getting excessive lift. And so we had a combination of drilling through the foundation from outside of the foundation just to get the polymer underneath into the stress bulb. We ran checks using Plaxis as a before and after to see what would happen, to see what we could achieve in terms of increased bearing, before and after, and what the performance would be. And checking our design with Heathrow, that looked like we could achieve what they were aiming for. And then we actually did some, these are the after results. You may not be able to read this, but the required bearing pressures were of the order of 270 to 330 kilonewtons a meter squared, quite an increase from the existing 160. And after our injections, all pad foundations had an increase in bearing capacity to more than 500 kilonewtons per meter squared. We far exceeded the required performance. So, and then we then also checked what the future settlement would be to make sure that, given the improvement and the increase in stiffness as well as increased bearing, would that be within their sort of tolerances? And all of the foundations passed their requirement for increased load. Here's a more interesting one about a historic castle. This is more to do with sort of a soil erosion problem as opposed to a bearing capacity issue. This shows a picture of Hurst Castle in southern England, where it's essentially, its origins are as a ancient castle for Henry VIII, but in sort of early Victorian times, it was modified to be a gun emplacement castle. Well, no, prior to Victoria, I think it was Napoleonic Wars era, which is prior to Victoria. That's when it was widely extended into essentially a gun emplacement castle. With behind each of those square doors, there would have been a cannon originally, a large cannon, and erosion of the actual sea had undermined part of this historic structure. And you can see there was a sort of catastrophic failure of part of the castle falling into the sea. Now, what we were asked to do is, could we do something underneath the remainder of the castle hadn't failed, because they were concerned that all the other sections of the castle were about to fall into the sea as well, because they were being undermined by the tides. So we did a trial injection on the beach right next to the castle, where we injected our polymer into the shingle on the beach. And after the trial, we excavated a couple of bulbs of polymer. This is 1735, one of our polymers, and you can see it comes out as really quite a large lump of solid polymer. And so the idea was, could we inject underneath the existing foundations to sort of create an extra solid layer under the older historic foundations? So first of all, we did a trial injection test on the beach, and that looked promising. We did some penetration testing to see, well, what sort of density improvement are we getting? So we were going from virtually nothing to like more than 40 blows for every 100 millimeter. So there was a substantial increase in the density. So that was also looking promising. We took some of the samples of this bulb of polymer, which was now a mixture of shingle from the beach and polymer. We had it tested in the lab, and we had an average compressive strength of nearly 3 megapascals. So the actual hardened polymer was really quite hard. So that also passed the requirements. So then moving forward, we came up with a treatment plan, and that was to inject either side of the failed section to stabilize that prior to coming back and redoing the section that had failed. And we have an injection layout like this, where what was required is where the soil under the foundation had been washed away by the sea. They basically put loose shingle underneath the foundation using a machine, and then we set in our injection tubes and we pump polymer underneath the foundation to stabilize it in situ. And so that was the work done. It was done using mobile injection unit and power unit. We had to work in between the tides because at high tides our injection locations were underwater, and so I think we did 120 tubes and 2.3 or 4 tons of polymer were put in, and it completely stabilized that structure with no further movement. Another one was on Calshot Castle, another historic England job, a little bit further down the coast. And here we had voiding developing behind or underneath some stone slabs, which were part of the sea defences. So in cross section, we have this voided area shown right next to the sea. And so this was essentially sea defence, and fines were being lost due to water coming in and out at high tide and washing fines out of the cracks in between the sort of sandstone sets. And again, it shows you just the scale of it. Not a huge area, but nonetheless, you could see that there was a section that was potentially slipping into the sea. And so we ended up with an injection plan to inject polymer into that void and stabilize the seawall. And that was also a successful project. This shows you the actual injection lances sitting in between the concrete sets. So that is the end of the presentation. We can now take questions with Alistair.
Thank you, Andy. Hopefully everyone found that very useful and engaging. Yeah, we've got a few minutes. There's quite a few questions, so I'm going to flick to this Q&A mode and see if I can bring these up. Okay, we'll try and get through as many of these as possible, Andy, but you can read these for yourself, but I'll read them out. Is this acceptable to building control after the foundations have settled?
Yes, because we don't actually alter the foundations. So for most projects, there's no real need to negotiate with building control because we're not adjusting the foundation, we're just improving the soil under the foundations. And then you can use further monitoring, PLM monitoring, to demonstrate there's been no further movement. So that's quite common.
Okay, thanks, Jeffrey. And then Alex has asked, can the injection improvement be used below industrial slabs where new mezzanine floor columns need to be supported?
Yes, they can, and we have done this in the past. So we can do localized injection underneath the floor slabs to increase the CPR, increase the density, such that you could actually then put point load on it with a mezzanine floor. We've done this on several projects.
Yeah, I think there's a couple of case studies on our website, Alex, if you want to have a look at those, but get in touch if you want more details. Are there any implications for disposal in terms of environment?
Yeah, a good question. This is relatively inert material and is not considered hazardous waste. So if you are to excavate and dispose of it in the future, it can go down to a normal waste disposal route. There's no need to take it through hazardous waste. So it can be disposed of in your normal refuse because it's very similar to most polyurethane type foams that don't require special measures.
Yep. Hopefully that answers your question, Callum. And then, David, how easily can it be excavated and cut when a site is redeveloped after it's been
well, it's relatively easily with normal construction equipment. It's not difficult to remove it once it's in situ. If you needed to re-excavate it, you can do it with normal construction type equipment. Yeah.
Yep. Question about the degradation and sort of the durability and lifespan.
Yeah, that's fair. Yeah. We've had now there's various studies been done on the longevity of polymers, and you can look in the literature as to how long do they last. Now, theoretically, we've seen research papers suggesting 120 years, typical lifespan. We have a BBA certificate for our treatments, and that's got a 60-year lifespan for the material durability. So anywhere between 60 and 120 years, possibly longer.
Yep. Thanks, Dominic. And then Hussein asks if the polymer can be injected in soil within a root protection area, something you're very familiar with.
Well, I believe so. Yes, we've used it on a lot of clay shrinkage jobs where there's trees involved, and there's no real need. It's going to be a lot less harmful than excavating a trench through a tree protection area.
Yep.
So as far as I'm aware, that's not an issue.
Okay, Eric asks if the polymer has been injected under a road, how resilient would it be if, say, a utility trench was cut through it? I.e., would the sides of the trench be stable?
They'd be more stable than if there wasn't any polymer there. That's what I would say. But if you want to design a trench using geopolymer to stabilize it, that's a different kettle of fish. But essentially, the soil will be more dense or more stiff than before. Therefore, it would be more stable than if it hadn't been treated.
Okay, David asks, how to establish in numerical terms what improvement in allowable bearing pressure achieved in its soils?
Yeah, well, I mean, we've developed some calculation methodologies, numerical models, which enable us to calculate the increase in bearing capacity based on the amount of injection that we've done. And that's essentially it's our sort of a commercial software that we've developed. I don't think there's anything available that you can purchase. This is stuff that we've developed and tested in the field. So essentially, we have our own bespoke calculation tools that do that. And if you have a project, I can show you an example.
Yep. And Ahmed asks, how does polymer affect fully consolidated soil sample?
Well, I'm not sure exactly what that means in terms of if we're talking a very, very stiff, very, very hard clay. The main route by which it could get into that is via any natural cracks or fissures. It's unlikely to fracture a very hard clay. But if you've got a very hard clay, you wouldn't necessarily be doing a geopolymer injection unless it's to mitigate things like clay shrinkage. And if that is the case, then there would be natural fissures present into which the polymer would move in a liquid state.
Yeah. Ben asked about lifting foundations and slabs. I think he may have asked that before we'd gone through your slides there, and so we probably
yes, we can lift. Well, I said we have a recent case where we lifted a pad foundation that was carrying 550 kilonewtons. We lifted it an inch so that we could lift foundations.
Okay. Nanas, if we provide a warranty for the work, if so, how long?
Well, we offer commercial terms on a warranty of typically 10 years. These are our current commercial offering on residential properties.
Yep.
10 years.
Okay. And David asks, voids identified by GPR or another method?
Yeah, I think identifying voids with GPR is a little bit hit and miss in my view. Best way of really identifying voids is by some sort of penetration testing, drilling holes and doing DCPs to actually prove there's a void. It's GPR is a little bit, in my view, a little bit suspect. It's always best once you've done a GPR to do some DCP testing afterwards to verify it.
Yep. Ben asks if it can be used for underpinning. Absolutely. We have a big residential business that deals with that. Colin, if the void below a road is caused by a sinkhole, broken sewer, what stops the polymer from disappearing down further voids or worsening?
Well, the key thing there is really to understand the scale and size of the void you're trying to fill. So if you know the dimensions of the likely void by penetration testing or site investigation, you would inject an injection scheme to prevent it just disappearing. You don't just turn up and start injecting. You need to have a plan, and you may do the injection in sequences, or you may consider partial filling of a void or a sinkhole with another material, loose granular fill or specialist lightweight fill materials to fill up the vast majority of the void, and then consolidate that with secondary injections. So you can use two different approaches to that.
Yep. John asks if there's any impact on rising water levels on floating material.
I don't think so. When we've installed it in the ground, it's bound into the soil. So it's not as though it's although it's less dense than water as a material, it's bound into the soil. such that the mass of the soil still has significant density, such that it would not be affected by flotation.
Okay. Paul, what is the typical spacing for injection points for strengthening of loose granular soils under building shallow foundations?
Typically a metre.
Yep. When using polymer and cohesive soils, how do you allow for the dissipation of poor water pressures?
Yeah, well, it doesn't really apply because we're operating in undrained conditions. So we operate, when you've got shallow foundations on cohesive soil, it's operating what I call undrained conditions. So pore pressures don't really dissipate because that's a long-term action. So in injecting our polymers, it's not really applicable, to be honest. It doesn't really come into the equation.
Okay, hopefully that answers that one, John. Then Claire's asked if the system is approved by LABC, Local Authority Building Control, or NHBC for new building housing schemes. I know we do a lot of work on new builds where there's been a construction failure.
Yeah, we do a lot of work for the NHBC, and we do a lot of work on social housing projects. So they're quite common customers of ours.
Yeah, so to answer that, we are approved for use. Dominic, what soil investigation techniques have you used to check sure improved soil properties? I mean, you've been through a few of those anyway, SPT, DCP.
Yeah.
Yeah. Pavlos, only one question exists. BS or ISO standards for the method?
There isn't actually an ISO standard or BS standard for this method. It's something that's a long-term objective of Geobear to get geopolymer design specified as an ISO standard. The only thing we have is a BBA certificate that relates to the material that to our design philosophy and our materials. So that's the BBA. So yes, it's the technology is too new, so it's relatively new for this type of standardization, but it's something that Geobear is working towards.
Yep. Norman, do you have any competitors? Well, there are new startup competitors, Norman, but we were the inventors of the solution. And there's originally we were called Eurotech. I think Andy touched on it, and Eurotech's franchised around the world delivering the same solutions. So, but in terms of direct competitors, then there may be a few, but they don't have probably the engineering depth that we do in terms of solutions for these sort of schemes we're talking about. Callum, can the geopolymer be broken down for recycling disposal? Clients may be worried that this is a new coal tar.
No, it's essentially polyurethane foams, really, and the polyurethane type based foams are ubiquitous in the environment. So that your car dashboard will be made out of very similar material. So these things are recycled in the normal way. They don't break down to form harmful compounds. So I don't think this is akin to a new coal tar, which polyaromatic hydrocarbons. It's not that level of doesn't present that level of risk because it's an inert material.
Okay, hopefully that answered that, Callum. Daniel, is the geopolymer affected by sulfates in the soil?
No.
Okay, we've got a few more. If we could do one line answers, Andy, then we'll try and get through them. Does the product undergo long-term creep?
No.
In some of your case studies, the original bearing pressure is higher than after the geopolymer is injected. Why is this happening?
I'm not familiar with those.
Okay, we'll have to review.
We'll have to have a look at that. You need to tell us which ones they are.
Yeah, Eric, drop us an email if you would, and then we can definitely have a look at that. How would geopolymer behave in a non-cohesive soil like peat?
Yeah, peat is more of a challenge, let me be honest, but we have alternative strategies for dealing with peat. We can either install a power pile solution, which is to pile through it and encase our polymer in a Kevlar sock, or we can use the displacement theory, and that's essentially to displace the peat with polymer and basically push it out of the way. So that's how we would deal with peat type materials.
Yep. Shalitha, can we use this to improve CBR in clay soils having CBR below 1%?
Yes, we can. And expected CBRs, well, at least 2, 4%, I think we would get. We'd have to look at the individual case and what the type of soil is, but significant improvement is likely.
Yeah, okay. And Gareth, would a solution using varying strengths of geopolymer be appropriate for an existing residential property, unreinforced shallow strip foundation spanning from limestone to clay? Would the solution be warranted by Geobear? And if so, what length of warranty would be provided? It's quite specific.
Yes, I think the short answer is yes. Send us the details. A 10-year warranty.
Yeah. What is the difference between geopolymer and grout injection?
Oh, there's a real difference in the material. Grout-based solutions are cement-based solutions, grout, whereas geopolymer is based out of polyurethane technology. So it's completely different chemistry.
There we go, Nan. Kelvin, if domestic warranty is around 10 years, how has this been received by the insurance industry? It's fairly standard, Kelvin. We work for all major insurers and loss adjusters, and that's perfectly acceptable and normal with them. And there is one last question from Gareth. Will the slide deck be circulated? Better still, I'm going to send over a recording of this webinar. I think there's a few sensitivities in the data on the slides that we wouldn't probably share widely, Andy.
Yeah, we'd have to check some commercial confidentiality. But if there's anyone has any problems, want to talk further, have got a problem in mind that they want just an opinion on, they're welcome to contact Geobear, and we will get back to them with a discussion.
Yeah, absolutely. So once this is processed, I will share this recording so you can watch it again or share it with anyone you want. And so look out for my email, Alistair Willis, later on today or early Monday. But thanks a lot, Andy. Thanks for everyone for joining us. So there was, I think, almost over 200 people there at some stage. So that was really useful. Hopefully everyone's taken something from it. That's all from us. We do run regular webinars on different subjects. So keep an eye on our website. And I think you might be added to a marketing list where you'll get a list of future webinars as well. So appreciate that, everyone. Yeah, many thanks. No, there we go. All the best, Andy. Cheers for doing that. Thank you, everyone.
Cheers, Al.
Okay, bye.
Bye.